So, welcome everyone. My name is Chris, if you don't know who I am.
Hi, Chris.
I work at SimWave. The reason why I wanted to have these talks is last October I went down to San Francisco for a conference called DMUX, and there are a bunch of different sort of talks about video, streaming video, capturing video, transcoding video, subtitles. There was a good 20-minute talk about Japanese subtitles at the last DMUX, which was an interesting talk. But yeah, so at the earlier point in the talk, they threw up a map and they're like, look at all these video tech meetings that we have. We have them in Seattle, we have them in New York, we have them in San Francisco, we have them in London, we have them in Berlin, we have them in Madrid, and there's nothing in Canada. So I was like, let's start something in Canada. Because I know a lot of people that I work with, they're all sort of passionate about video and they'd be good at talking about it. So yeah, so before we start, thank you for Abdul for letting us use this space. And thank you to DMUX for the pizza. As part of the conference fee, you get to sort of run startups and they help pitch in a little.
Oh, so this is sort of an official franchise of the DMUX?
Yeah, we're video tech, and so there's a video tech Slack where like a lot of people who know stuff about video talk about video. So yeah, so our first speaker is Eric. So we'll have to welcome up, and he's going to be talking to us about video coding open source hardware.
Hello, I see I know a few faces here, but my name is Eric Pearson. My background is in hardware design, so I design chips as well as FPGAs, right, as well as boards and stuff. But so I'm in semiconductors. And so what I'd like to talk today about is a sort of a bit of an orphan standard, the web video coding, Mpeg WebVC Coding, as well as some of my thoughts on open source hardware. I'm looking around for an open source hardware project, right? And I'm getting some, anyways, I'm finding some interesting things. And one of the projects I was looking at, so I'm sort of settling on this standard, is something I'd like to implement as an open source project. So what I'll talk today a bit about is Mpeg WebVC. Chris said this was a series they wanted details. So I'm going to talk about some key features. Then I'm going to go through every last detail of the standard in 7 slides. Let's see if we can do it, hopefully 7 minutes, right? Then I'm going to talk a bit about what I'm thinking about open hardware. So going a little bit about what is open source hardware, what I've seen. Maybe some of you have got experience with open source hardware, maybe some of them are different, but what I've seen. And then talk a little bit about, well, if we're going to look at a hardware encoder, you got to go, well, why bother? You get them embedded in chips, you run software ones. What's unique about hardware? Well, one of the things we do with it is latency. I can shrink latency down to almost nothing, right? So that'd be interesting. I have a few projects I could do with a sub-millisecond encoder, right? So. And then just touch a bit on the architecture of this design. So really just the outer block diagram. In theory, Chris gave me almost 2 months warning, and I should have had the whole design done by now. But, things got in the way. So this is just a paper exercise at this point. But I'm trying to give you some data in the middle here that's real. And some of you will have seen it all before, maybe, but this will be a different perspective on it. And others will just give you a feel for what WebVC is and how easy it is, really. Okay, WebVC is really just ABC, H.264, but it's the constrained baseline subset, so the core profile that is compatible with every single decoder out there. It was created as a spin-off spec, so the editors took the ABC spec. I was one of the editors, so I kind of like this, and took it and took out everything to do with anything other than the core constrained baseline. The idea was they wanted something that could be royalty-free. I don't think that's ever going to occur, right? You have to get everybody in the world to agree not to charge royalties on something to make it royalty-free. So there will always, I don't know even know if the licensing authorities or the licensing bodies have agreed to royalty-free it, but for an open source design, I'd go with this, right? Reasonable use terms of of patented material would allow a single experimenter to build one on their own. Just don't go commercial with it. Let's see, what else do I like here? It is compatible with all AVC decoders. If you build an encoder, it's pretty interesting. Building a decoder is kind of useless. If you build a WebVC decoder, it can only decode this very restricted version of H.264. And so I was looking for open source hardware, and as I said, I've chosen this because I could do a low latency, as well as it's lower complexity, the whole AVC standard. But this is a standalone spec. It's about this thick. Versus last time I printed out H.264 was pushing maybe 3 inches, right, with all the SVC extensions and stuff. Okay, WebVC versus AVC. Somehow this thing changed. They changed the font size for the tiles. It used to be a lot bigger.
Okay.
So I don't know what happened there. So what is WebVC? It's really a subset of 420 8-bit IP coded only, so there's no B frames. And with CAVLC coding, which we'll get into a bit, only has a few macro block types, pulse code modulation, basically, as well as intra 4x4 and intra 16x16 prediction of the blocks, and as well as some intra prediction on 16x16 basis and 8x8 basis. I'll get into some of these words in a minute here. Don't worry about it, right? You'll figure it out if you know it, or else you already know it. Does not support some of the AVC tools like B slices, which are quite handy, 10-bit, 422, codec, interlace fields, as well as a picture adaptive frame field, as well as macro block adaptive frame field. All these things just go away, right? This is just a simple frame encoder. You have no weighted pred, you don't have 8x8 transform scaling, list slice groups, all sorts of fun things, right? Standard is there. There are some reasonable, or some profile limits that are unique to this standard, which says if you have PCM pals, you can't have zero value pixels. So some odd thing, so you just stay away from zero value pixels or kick zeros up into ones. You can only get coefficients so big, so you gotta watch out in some cases. So I think the maximum coefficient range is 2063. The profiles, the levels are only specified up to 5.1, so that really gives us, you can only sort of interoperate with everybody in the world at 4K P30 or 1080p at 120 frames per second, sort of the max it could do. And it can't do bit rates over 288 megabits, which if we're talking about a low latency encoder, we'll probably need those. Okay, so now I'm going to dive in, and we're going to go look at a little bit of detail here. Bear with me, and we'll try and get through it. And the idea is give you a feel for the standard, right? I don't have every detail here, but I got most of them. Okay, pictures and streams. Pictures are divided up into rasters of 16 by 16 macro blocks, where a raw macro block in 420, which is a video standard, involves 384 bytes. That's 256 bytes for the 16 by 16 Luma, as well as 64 by 64 blocks of chroma 2 of those. Frames of video are encoded in a bit stream. Bit streams are actually rate limited in terms of there's a maximum bit rate, but saying a bit rate by itself is meaningless. You have to have a sort of a model that talks about a buffer size, right? So there is an HRD model, parameters by byte rate and a buffer size, and assuming instantaneous decode, and then you have to be able to transmit your data without overflowing or underflowing that buffer. So you can actually transmit to somewhere else on the planet and have it get there without hiccups. Byte streams, which are which is what really transmitted, are segmented to nulls by start codes. Over on the right there, it's a 001 as a start code in the stream. So you detect that you've got one of these packets. There are SPS and PPS that describe stream info or picture from all those are packets that are quite important. So they actually use 3 zeros in front of them for the start code, so you can find them quicker. And then there's emulation prevention, which allows us to basically prevent start codes from being found in your bit stream. During the generation of your stream with these variable length codes, you might accidentally generate those. So this is why they embed emulation prevention a 3 byte. And that's probably why the PCM didn't allow 0 bytes in the data, because it's just put in the stream as raw bytes. Slices are shown here. They contain a slice header followed by the macro blocks in the stream, and the picture or whatever the slice, you can divide it into slices. And then each macro block consists of, well, on P frames, consists of a skip, or on I frames you don't have skip because there's going to be data. And then you either get a PCM block, which contains the byte alignment plus all the bulk data. Intra 4 contains the 16 rev and primos. Yeah, this all reformatted things somehow here. It was my format. I should have done it as PDF or something. I'll learn. We got Intra 16, where we have 24 different modes, but that embeds in it as well the Intra 16 modes, as well as the coded block pattern. And this is the, I think that is the chroma predict. I think I'm Intra chroma prediction mode. Yeah, the M is below. Okay, QP delta, as well as then we got DC transform blocks, AC transform blocks, as well as chroma DC blocks. We have P inter, which is basically a motion vector, and so we contain a reference IDX, as well as motion vectors, up to 2 of them, as well as our coded block pattern, which says where the coefficients are grossly in the block. QP delta, which is a quality parameter, followed by coefficients. 8 by 8 is basically allows us to recurse down. There we have subtypes to say what the shape is of the subblock, as well as for each of those, the reference IDXs, the motion vectors, CVP, and the QP delta. And then we've got the beautiful one that we're always trying to code, which is the skip. And the skip run is just the theoretical. It says, how many macro blocks do we skip? And just do the default coding of them. We'll get to what that means, but it's really going, follow the motion vector of your neighbors and use this, just copy the same motion vector and use that as a predictor and don't have any coefficients to correct it. So it's really, if your scene has slow movement or something, you probably skip the whole thing. Just do the motion vector in the upper left-hand corner and it will be inherited throughout the frame. That's the first one.
Sorry.
Okay, VLC coding. So that's how we put integers or symbols into the stream. They try and design them. I guess these are Huffman codes, tables where you want the highest probability symbols to be coded with a few bits. And so what they typically, sorry, hey, this looks great on my screen. And so really the most simple one is like a unary code, which is just a binary code. So here, it's basically unary code 0 to 7, just binary code. It's the simplest one. But they use that sometimes in the standard, as well as they use these UE or EXP Coulomb codes, which are variable length, and they're optimized for the fewest bits for the smallest values. So the whole standard is based around, let's get small values. We want to predict motion vectors. We want to predict the pixels themselves. And so we're always trying to get values down near 0. And so smaller values, smaller things. So this is just an example of a picture parameter set. It just talks about things you can code in the information. We see in things like there. Is there anything we recognize? Whether deblocking is turned on or not. But these are flags and integers coded in the stream. But you can see the coding styles are just listed there. So it's very easy to read the standard and figure out how to build a parser or an encoder for this. So it's VLC coding. They do sometimes they go, well, sometimes my integers aren't in the right order. My most probable symbol isn't the 0. So what they do is they put it through a lookup table, and they'll read that. So this is VLC coding. Then we have CAVLC coding. This is what gives it its, step above Mpeg a little bit, was the fact that we do context-adapted coding. And it's really done 4 ways. But basically we deal with the coefficient level. They start doing what do we call it? It's a state variable. As you start to code symbols, like let me step back a sec here. So we have our transfer block in the upper right-hand corner. We're going to snake from DC down to AC. So we turn a 4x4 transform block of coefficients into a linear string. And so here I plotted one on the bottom, for example. And as they start coding the symbols backwards from the tail end up, and then they go, as soon as they get a symbol that's a bit larger, they switch to a more efficient coding for larger symbols. So they shift gears from suffix length 0 to suffix length 6. As well as there are also the next one is the coefficient token, is the one that really says how many non-zero coefficients there are. And they also coded into that how many trailing ones. So you get the efficiency of when you code multiple symbols into one integer, you usually get an efficiency gain in coding, right? Or that's their intent. And so they've done that with the coefficient token. Total zeros and run before are basically examples of total zeros, so that's how many zeros there are, so there's 7 in this case. But then you can sort of optimize the run before a bit and change the symbol coding to go, well, how many zeros do I have left? I can change the VLC code table to use there. So it adapts down. But through this is what they call CAVLC coding. It's used in other standards, but it's the basis that helps us get our lossless compression, video compression. This is not losing any information. This is just trying to represent the information in the tightest way possible. Well, basically the codec is built up on the main concept is the decoder can build a prediction of what the current macro block will look like before it's received the data, before it's received the coefficient data, and then later on that's going to be coded as the coefficients in the bit stream. So there are 2 types of prediction. That's Intra Prediction, which is predicting on the same frame from the neighbors. And we'll get to Intra Prediction in a second, which is predicting from past frames. So, Intra Prediction on macro block. Oh, this is Intra Prediction. Sorry, I usually start with Intra, but no problem. This is Intra Prediction. For P frames, you can use Intra Prediction. They have up to support a maximum of 16 reference frames. You typically wouldn't use that, and it's also limited if your DPB is not big enough. The macro blocks can be partitioned, so in the upper right there, I've got the 16 by 16, or else it's 8 by 16, 16 by 8s, or 8 by 8s. And once you get down to 8 by 8s, you can subdivide those down further. So you can have up to 16 motion vectors per macro block. There is an obscure specification that says on average you can only use 8, so watch out there. Each differential motion vector has a dx, dy, and a ref idx as to which frame it comes from, and the x and the y. The resolution is quarter pel. And so our x's are quite large, up to 2K, plus or minus 2K, y is 512, plus or minus 512. You might be limited on 4K images a bit by that. The motion vectors themselves the motion vector differentials are what's sent in the bit stream, but the predicted value of those motion vectors is inherited from the neighbors. In specific cases for the 8 by 16 and 16 by 8 blocks, they tell you where they come from. However, what you typically use, and it's often used throughout H.264, you have this neighborhood of A, B, C, D, and in this case, they've actually taken the median of three motion vectors from the neighbors. And I always go, well, how do you take the median of a point? Well, they really did it the median of the x's and the median of the y values. That's what's in the standard. And then, so you got these predicted motion vectors, and the skipped macro blocks I mentioned earlier is one that would just use the predicted motion vector for the 16 by 16 block. Luma, we have to have sub-pel interpolation, and so that's part of the standard. So Luma has quarter pel interpolation. It's a two-part process. The first half we use 6-tap filters, both horizontally and vertically, to generate half-pel values. And then after that, we take the half-pel values and the integer values, and we do simple interpolation between pairs of values to fill in the quarter-pel numbers. So it's a 2-step. You got to interpolate, filter to generate your half-pel values, and then interpolate to generate your quarter-pel values. For chroma, it was just simply bilinear interpolation to use the 4 corner values. So from this, from the motion vector differentials in the bit stream, we're able to reconstruct and create prediction blocks using these mechanisms for the macro blocks themselves. Then there's also Intra Prediction, which is going if it's a new object that the neighboring pels have no value to contribute to, or sorry, if the pass frames have no value to contribute to, it's like something appearing suddenly. Well, then you got to start describing with what you got, and like Mpeg, I think simply just used I don't even know what it used, fixed value. I can't remember.
It was coefficients, I think, the neighbors or something like that.
Something was used, right? So DC prediction. But what they have here is they've got, so Intra 4 is basically using, we predict every 4 by 4 block, is this diagram, and we take the neighboring pels, and you can either pick a direction that you're going to project these neighboring pels. So these pels are outside the macro block, and you can project at different angles to fill in, interpolate those values. So it's projecting the data in, and they actually select up to 8 different angles, or DC. And so really the 13 pels, you have a neighbor on each block, and including for Intra 4, you got to get some from the macro block in the upper right. You can project these angles. Intra 16 Luma only has 4 modes. There's horizontal, you project, vertical, take the DC, or planar. Planar is kind of a fun one, which fits a line to each edge of data, and then you just define a plane based on those two straight lines. Intrachroma is similar, although it just predicts from the 17 neighbor pels. So we now have 2 tools. We can generate our macro block prediction from either historical frames or from the current frame, right? If it's new data, you got to do it from the current frame. And then you need to now compress this. And so that's really, so what the standard describes is how to uncompress it, so I won't go into how to compress it here. But it's really just this backwards. So the first thing you do is you've got to inverse quantize it. So it has been, so the idea of QP is how much you scale these coefficients. So what we're going to do is we're going to get in a set of coefficients from the bit stream, a 4x4 matrix. We know how to have and we will have a QP value, which is a quality parameter. The quality parameter varies typically from 0 to 51 in the standard. And what it does is every time it steps by 6, it will double the amount you're scaling up the coefficients. So what we're doing is make them larger. But if you have a low QP, which is for high accuracy video, that means that every coefficient step is only changing the pixel value a small amount. So you get the finest control, whereas it's really the size of the bricks you do to fill up between what the image you want and what your predictor says it is. And so high QPs make these steps very large. And so what they are is they're scaled. And the interesting thing is they've got both the scaling that's required by QP, which is that simple equation up at the top where it's QP shifted left, shifting left this other value, but it's also by this level scale matrix, and that's sort of this non-uniform scaling matrix. And what they've done is they're using, next step we're going to use an integer transform to do the inverse DCT, but I don't think you can do it with an integer, or not without large integer values. And so what they've done is they've done some scaling to make the data non-flat, and that's part of the DCT is incorporated into the scaling. And then we do a 4x4 transform. They basically defined it as, that diagram almost turned out right, as basically a butterfly that we apply to all the columns and all the rows of the image, and thus we've done the inverse, at that point we've done the inverse DCT. And then, just to make things a little bit slicker, they also said for Intra 16 and for Chroma, they also then do a further transform on the DC coefficients. This allows you to take what they figure is probably a lot of these DC values were all the same, rather than transmitting, and they're typically large DC are the big ones. And so what they're doing is they're saying, well, why don't we transform it? And that will put, if they're all the same, that will put it all into one single coefficient, all that information. So it's trying to pack further information here. So this is the lossy part of the codec. And then the last thing is a final rounding right shift, because we've done all these multiplies to make things very large, and so right shift by 64 in the end. And we now have our reconstructor, our residual, which is what the decoder will see that he can apply. He can take this residual and add it to the predictor, and he'll get what the encoder wants. So it's just simply add after this. And then the final nice step that they incorporated in was in-loop deblocking. This is a small part of the standard, but I always find it kind of complex. But basically, the purpose is all these transforms are going to create block edges on the transforms. And that's just a bit ugly. So what they did was they said, let's go through every edge, every 4x4 edge is a candidate for deblocking. And they said they'll define it as a, defined as traversal of the 4x4 block edges. And what they do is they figure out what a block strength is, and that's really sort of say, how much should we filter? And they go, well, if it's PCN, well, don't filter it. If it's intra, well, we better filter it heavily. It's going to be wrong and blocking all over the place. It's not a very good prediction. If it's two disparate motion vectors, well, you better deblock that. There's two motion vectors almost the same. They actually define almost. And then it says, well, don't do much filtering there. That's probably, and I guess there's two filters that are identical, and it says you don't filter it, right? Or very light filtering. And so so we determine block strength, and then we have to determine whether we're actually going to filter that individual pixel or across that edge. So it's basically, we're going to filter right across that edge there, and so I've blown that up. And what they have is they have an edge detector based on some parameters you provide, as well as they're scaled by the size of QP. But it says, is this really an edge? Are there two flat spots that are less than beta on either side? And is there a step that's greater than alpha? So this allows you to sort of, or it's actually a step less than alpha, I think, is because if it's too big of a step, you go, well, that's probably a real edge. I shouldn't be filtering that out. I may have that backwards, or my Tom's a bit wrong there. But basically, those scales, you can offset them with parameters in your picture parameter set, as well as, and so what happens is it goes through, does all these filters, and determines at that point what the block strength is, and then applies the filter. So I have an example here of block strength 1, I just showed it, just simply lowers the points and raises the other one, whereas a block strength 4 is a full 4 or 5 point filter that just really hammers on it and modifies up to 3 of the pixels. The problem is this is defined as done in place. So everything's recursive, not within the filter itself, but when you're traversing this whole thing, if you filter across this edge, that's going to affect the pels that are on that edge. So you've got to watch out your parallelism here. You can only do so much parallel. And then there's also an issue that it forces your whole image a bit to the right and down. So you have to take care of, if you're doing a macro block processing pipeline, you're never going to actually be able to finish your macro block because you need the macro block to the right of you to filter with. So there's going to be partially filtered pictures. Okay, so I think that's covered. Those 7 slides really did cover all of WebVC. And so what the purpose was is to show you not that bad, right? It's a lot simpler than the full AVC and all of its rules just explode in complexity, right? So this is a nice straightforward, but it's still got the fairly advanced features, right? So I think I missed a few things, or I didn't cover certain things like maintaining your decoder picture buffers. I didn't talk about levels and stuff, but I was only interested in the top level. And then you wouldn't be able to actually implement it from the slide step, but you would be comfortable going through the standard, I think, is my hope, my purpose. Now I'll talk a little bit about hardware. Okay. I've been disappointed with all open source hardware I found. I've been using it for years. It's just small fragments of code up on the internet, right? Or developer boards, or like the RISC-V, there's a CPU that's open, right? That was just a standard, right? It's stuff I can't rely upon. I can't try it out, right? It's just somebody wrote as a lab assignment, wrote up how to do a matrix multiply. I'm going, I don't need that, right? What I want is a working system that I can get working right away. But then again, the boards you run these things on, FPGA boards, and I've seen FPGAs in multiples of tens of thousands of dollars for the chip, right? These development boards are insanely expensive. So what has changed in the last 2 years is cloud FPGAs are out there. And so they're coming from multiple vendors. And so this is sort of, I think, just completely dropped the barrier. So now, what we can do is you can do a design of something complete that actually works and actually does something, and then somebody else can reproduce that for a very low cost, probably $5. Right? And so, because I get the tools, I can rent a computer capable of running the tools for 25 cents an hour. A typical run might be 10 hours. If it's good, sometimes it's 50 hours, right? But for a 5-10 hour run, and you could rent the FPGA board for $1.50 an hour and that's billed by the second. So I would often use it just for 10 minutes, try it out, shut it down, timer stops. So what it's done is it's a platform now that I'm so jealous of what open source software people. They can download the stuff, get it to run right away. It does something wonderful, and they can modify it, and they're up and going, right? They don't have a big expense. So I think this is almost enabled that, right? So it's a big change. So it's been a couple of years now. They've been out. What I'm looking at is, I think that I was looking around for open source hardware projects. I've got involved with another one of those and trying to learn what's going on, what it means. They had embraced the whole cloud FPGA thing as the right way. So I was looking for a project, and I think a sub-millisecond latency WebVC hardware encoder would be something that takes advantage of the hardware, does something useful. I'm sure you can think of uses for something where you want a very low latency, So it really takes advantage of it. As long as you support accessible cloud targets and build environments that enable experimenters to use it, maybe some will actually use it, right? It won't just sit there as some library and some companies try and collect them up as over an open source company or something, but rather it would be something useful. So this is what I'm looking at. So let's talk a little bit about what low latency means. I probably have this wrong, but it's the key thing of a key value statement of this. So we have to figure out why I reformatted everything. I thought PowerPoint was no, I guess not.
Yeah.
Probably the shape of the screen was different, and I went, oh, I'm going to reformat stuff. And so, I mean, you can talk about latency through the system. You can say, well, it's from glass to glass. You know, at 1080p 60, a macro block time is 2 microseconds. Close enough. You know, camera latency can be quite a while if you have a framed shot of a camera, but really, if you have a rolling shutter, which is the exposure is just preceding the scan over the line, you can get that down close to 0. So I'm not going to count the camera scan time. Still have to convert the raster, assuming it's a raster, although there are cameras that aren't raster. If you go to Dulce or Teledyne, I think they're called now, they have all sorts of formats of cameras, and you can get out PELs pretty darn quick in different ways, so you don't have to go through this. But assuming it's a raster camera, it's 24 milliseconds to get an entire, or sorry, 24 quarter of a millisecond to get out, convert one macro block row of your 1080p image to capture it in raster and then start outputting it in as macro blocks. Then we can build up a macro block and code pipeline. And so I'm looking at if we do some buffering, do some stats, do some hierarchical motion estimation, do some full motion estimation, do some sub-PEL motion estimation, inter-estimation, and mode decision, transform quant and inverse transform, do the variable length coding, which is the CAVLC we mentioned, as well as do a VLE to get an idea of how big that block is the first time you encode it. So I was talking about multipass. And then we have a look ahead, get our rate control there so we have a chance of getting our rate within our 288 megabit limit at this rate, and then re-encode it again and output the values. So I'm going, I think that if we take an entire row of latency, I think we turn out just fine here. So looking at a quarter millisecond there. Communications delay, well, I really can't count that, or I don't know. That's not something I can control, right? That can be bouncing off of a satellite, right? And then the decode, well, if you take a normal decoder, it would be, if according to the HRD model, it waits for all the data to arrive and then decodes it in 0 time. So we can say that's going to take, if we're assuming it's transmitted at this rate, it's 24 milliseconds, though most decoders will start in or they can start in your data early. Of course, depending on how you set up, it might be many slices before it gets to it, right? So it really depends on whether there's an optimized decoder or not, but I think that's plugged in. And then I think I got the last one wrong, but as taking the macro block outputs to a raster to get it back to your display. I have a feeling, I think that count is counteracted. I think I'm double counting this raster delay there. But overall, though, I think we can get under 1 millisecond is a reasonable target here.
But counting the raster delay for like the motion vector size, like say let's do 0 for this, let's say depending on.
Well, that's a previous frame. These are macro blocks.
Right.
So the previous frame is there.
But if you're counting at 0, you need to have the whole previous frame. Right?
Yeah, so you do have the full previous frames. Guaranteed. Unless, well, actually, except for maybe one macro block row, but I don't.
Yeah, that's what I mean. Look,
the vertical,
yeah,
but it's only one macro block. It's only one macro block row, and the vertical motion vectors are only 512. So I don't think we got your reference in front. We're not. They don't support fields. So thankfully we.
Okay.
So I think it's feasible. Now, I didn't go into detailed architecture of this, but I did write down a few architectural requirements for myself. So try and go, well, what would be, you know, put on my quote marketing hat or whatever. What would be useful, right? On 288 megabit, let's have this thing so it can do full flat out, quarter millisecond, 1080p 60. 4208-bit WebVC encoder, have some programming that support different picture sizes, Support a raw macro block input so that we get a very low latency there, but you can always have read from memory as well done externally. Set our macro block rate at 500 kilohertz, so it gives us 2 milliseconds or 2 microseconds. Have a programmable macro block pipeline depth, so you can actually shorten your latency by a little bit if you want. Codec is looking for, so I was trying to go, what type of codec? Well, if you're doing low latency, you really can't afford, well, you can afford, with your rate control, you can't afford iframes. Because an iframe is a giant amount of data, so pick a number of 10x larger than p-frames. But my rate control is only over a 1 macro block row. I can't, so I would be unable to move. What you want to be able to do is move pixels from your p-frames and move them, allow them to be used on your iframes. But if we're coding this quickly, we can't do that. So what we do is we use a dual pass coder I've already mentioned, but with intra-column refresh. So you have every frame, there's guaranteed 1 column of all intra-blocks, and that keeps progressing to the right. And so basically, if you watch the video for more than 120 frames, it will start anywhere. It'll be within 120 frames, it will probably refresh your entire scene, and so you'll now have correct reference frames. Really, that's just controlling the motion vectors when you're on either side of that to not cross that intra-row or intra-column. Like a per macro block quality target input, so that if you know things about your video or areas of your video where you want more detail, that can easily be coded at a macro block level. Output is a byte stream and a DMA ring buffer, multi-port memory interface, 40-bit addressing, and 512-bit reads and writes. 30-bit control bus, single 256 megahertz clock. Of course, I use PLLs inside to get higher rates. Programmable interrupt, and then there's this whole. The only thing one of the things I've learned about the open source is picking your correct licensing terms. Right? I'm kind of biasing towards the copyleft, as that seems to be more the spirit that forces release of your source code. If you use this code, it forces you to release your source code as well, right? I believe this, but copyleft is the terminology is used there. Okay, Chris is nodding, so maybe we got it right. So I'm leaning towards copyleft. Anyways, hopefully you got something out of this. Cool. That's it. That's it for my presentation.
Any questions?
So latency is the benefit. We obviously see it 1 millisecond, very impressive. What's the catch? Quality.
Yes, obviously. I said 280 megabits.
Yeah.
But the thing about this is I think hobbyists can work with video codecs. You don't need a science team as long as you just turn the bit rate up. Right? I can make my video look as good as your video. I just take double the bits. I'm not worried about that. So I think 288 megabits is what my target is. Do you think that's enough?
So that's about, 1080 and 60 is about 380 gigabits per second.
So it's about a 10 to 1 compression.
Yeah, so image compression can get you about 10 to 1 compression. So why build so fancy tools if you can get that level of compression using iframes? So images typically will get you 5 to 10 times if you use, let's say, JPEG 2000, which is complex, but or JPEG. So we have a lot of fancy tools here, as you said. And it's a video compression approach, and we have keyframes, but the compression ratio is 10 to 1, which is really low.
Well, then I'll turn the rate down.
Yeah.
Right? I mean, so I am targeting 90% are P macro blocks, over 90%, right? So sorry, 99% of the macro blocks are P macro blocks. So I should be getting better, depending on the scene, right? What's happening? If it's horses running in water, or who knows what, I'm going to get there, right? But if it's a static image or slowly moving with a large scene frame, a large scene slowly moving, let's say, not even necessarily slowly moving, right? Off the front of your drone. So really here the advantage is latency. Sure, you can try to do it all eye, but this will beat an all eye because this has P references. It's really a matter of how the rate control works out there.
And rate control, QP on a macro block level gives you a lot of flexibility.
Yeah, and we've done, it's just you don't have time to, I mean, often we've applied things like AI to the frame to find interesting things and turn off the, that's the biggest trick in the world, right? And turn turn down the QT when something interesting is there, but I don't think you have time at these sort of latencies to run that. But if you have fixed patterns like a security camera where this is interesting, this isn't, you could just knock the QT down in areas where it doesn't matter.
So just out of curiosity, there must be run length. Is there run length coding as well that just gives you additional gain at the end or not? After CAVLC?
No.
Not needed?
No. Well, no, there is. It's a standard, and no, there's not. There's nothing else.
So from a stack perspective, what configurability is available? So typically you would have some software with a driver, with firmware, with ASIC that could be programmed.
I mean, sorry, which software stack? You're asking which software stack? Well, if you're interested in contributing, I'll talk to you about it, right? But I mean, I hear that everybody just wants FFmpeg. You know, I don't know how hard that would be to do. I know ways probably not to do it, but probably my own driver, right? It's very easy for these boards to get access to it. And just, I think from an example case, make it useful enough so I can read a file from have a simple C script to read image file into memory, and then just use basically these big FPGAs have all the DMA and tools to move data down to the FPGA memory and make it accessible. So if I get it encoding at the time rate, I think, and make the software clear enough and simple enough, I think people could extend it to add FFmpeg in the end run, right? But I would start with something simple. Thanks.
Is this meant to be streamed outside of the container format, or is that the whole muxing of it? And
I just put out here a byte stream. So I mean, in terms of TS packaging, I haven't looked at that. So that would be outside. Right. That would be in your app, right? So normally for FFmpeg, that would be you'd have a streamer. Yeah. After this, and then you'd have servers running to.
But there's nothing in the WebVC standard about
WebVC,
how to.
No, that'd be a streaming. That'd be the streaming standards, right? The WebVC. There are some annexes that allow you to describe your frame rate and such to those tools with the DUR grammars. It's the same as H.264. So
there's like the HAP timing model that you can provide.
Yep. I think it's the BUI parameters. Yeah. So that's still part of the standard. I didn't cover that as well. Oh.
So WebVC is basically a subsection of the H.264 standard. How come it ended up being the royalty free? I didn't get that.
Well, that was their goal, right? So what they did was they said we'd like to drop the barriers to people using ADC. And so what they had this idea, which said, well, let's carve out constrained baseline. And they said, well, first of all, people started looking, well, I don't know what that is. I've got my IP in there and then the H.264 standard. So they got convinced to strip out everything else. So we actually got a simplified standard of this. But I don't believe anybody's going to sign off royalty free on it. But I mean, I think under fair use terms, as hobbyists, anybody can use this stuff, right? Just don't go commercial without going to see. You probably have to buy an ABC license if you made a professional coder like this, right?
The original goal while H.264 was being developed was from the very beginning that it would be royalty free or have a royalty free baseline, and then other tools started to get added that were not royalty free. They were coming from companies that would not give that their IP for that. Then part of the group that was kind of like core original group, especially the ones that were doing like the Polycoms and Telenors that were doing like the video conferencing stuff, they then kind of tried to carve out this like sub baseline thing that was called the constraint baseline. That was kind of going back to the original spec, which interestingly enough fit on 7 pages, the first draft of it. So your 7th slide is very perfect.
Thank you very much. All right.
Great. Thanks.
So that's other codecs.
How's our time go?
It's good. So the next presentation is from. Gotta go fast. Pim.
This is going to be a lot less technical. And and a lot less professional as well, so bear with me on that one. But I was told to try to keep it around like 15-20 minutes, so we'll try to keep it there. So yeah, my name's Pim. I work at Vidyard, startup in downtown Kitchener. Some of you might have heard about it. I am by no means a subject matter expert. I'm counting on you guys to be subject matter experts and tell me all the things that I did terribly. But I love memes and making hacky things. So quick side note, what I mean personalized video, I can group them sort of into two categories. One is one-to-many videos, where you produce it once, many people can consume it. The other would be what our solutions consultant here is doing, where he's reached out to one person. So it's like a one-to-one video is the kind of idea behind it. And I'm going to be talking about the hybrid of the two, where you make a video template and then make it so that it's intended for one person. So it's like a one-to-many, but still has that personalization piece of it. So those are the ones that I want to talk about. But yeah, like how do you do that? So current industry standard, I think, is kind of just to use something like an After Effects project and then have places in the project where you can then personalize those. And then we have some scripting that will then invoke After Effects for the different pieces of personalization, and that gives us an actual MP4 that we can then send down to everybody that we need to. But there's some problems with that approach, because one is then you need to store all the different versions of those video files. You also need to render all the different versions of those video files, and it all needs to be done ahead of time. So a lot of these projects, when companies that make these kinds of personalized videos to reach out to them, have done it in a way that they're sending it out via like an email campaign. Because they're really trying to like break through the monotony of email. And if your name is on the video, you're like, ooh, what's this? And you want to click it. So they're trying to do that. And email campaigns being a big thing means that we now need to render like 20,000 versions of a video before they can even send the email out. So also, this has been my experience with Adobe products. So if we could just like, not use that, that would be great. So the investigation around the beginning of this was to like, okay, well, if there was a way that we could, like not use Adobe, what would be the alternatives around that? So when I was looking into it, the After Effects, Premiere Pro, those kinds of things are like industry standard in terms of what companies tend to use to produce video content. So it was difficult. There didn't appear to be a ton of options around like being able to produce video content out there. And even if there were, I feel like it would be difficult to convince our clients to go and use some software like maybe Blender or something like that to go and produce videos. So, but After Effects has like a scripting thing in it, and you can make plugins for it. So like ImageMagick does like ImageMagick stuff. Like what if I like take an AE project, use my like plugin scripting stuff to figure out what After Effects would be doing, and then just do all that stuff, but not in After Effects. So, not saying it's a great idea, but basically it was like, well, like video, like, I mean, I hadn't been a video at a terribly long period of time, so completely naive, figured like video is like a couple frames, there's different kinds of frames, but like they're all just like pictures after one another. So like if I just render all of these pictures at the same time, like yeah, it's like a lot of compute power, but like then they're all at the same time. And then I just combine those later. Then I have a video. So yeah, it takes more resources, but then like I would have instant video. And if I choose some smart things that are like parallelize everything, like basically like choose HLS, because then I can also not only like do all the frames at the same time, but when certain groups of frames are done, I can also like encode those at the same time. So now I have like portions of the video encoding at the same time rather than trying to do the whole thing in one go. And an added benefit to that as well is that like when you have a personalized video, generally like there's a whole bunch of the video that's not needing to be personalized. You have like, these pieces of the video that are just like static from one thing to the next, then you have one piece of the video like a name on an iPad that you do need to personalize. Well, if we take the HLS stream and segment it so that the static pieces are like, I don't care, and then I only need to render these pieces, now my manifest can actually include like all this stuff at the beginning of my manifest file. Like, sorry, am I going crazy for like, HLS? People, sorry, yes, no, yeah, HLS. Cool. All right, cool. No, I'm just thinking like format of HLS. If nobody knows what it is, I'm going to be lost. So yeah, I keep those ones at the beginning of the manifest, and then I can send that like partial manifest down to the player, and now I'm basically just live streaming a video to their browser, rendering this shit, and that's just like a bunch of frames. Do those all at the same time. Each of those frames are going to have like a piece that I just like manipulate, put together, got a frame, excellent. Take those frames, get some audio, and then shove those together, and I got a piece. and then bam, stick those in the manifest in the right order, and I've live streamed this to the person's player, and they're watching a video. So that was my idea. I made a proof of concept, and then I shipped it to my boss, and they said, like, this is great, let's do this. And then I was like, cool, and I built it. This is not the first iteration. It looks a little messy, but yeah, we won't get into those. But the idea is that this is not the first or final, probably, iteration of this, but the general sense is that like I have one thing that's sitting on the web, and then I have a bunch of different Lambda sort of workers and queues in front of them, so that I mentioned before, email campaigns come in. When an email campaign comes in, generally it ends up looking like a lot of people, when they receive their email, will open it within the first like 15 minutes of receiving it. And if you send out 20,000 emails in one go, and then let's say 5% of those people start clicking through, and then you do all of that within the first 15 minutes, you're going to have a lot of videos that you need to render in one go. So Lambda was not my first choice, but very quickly afterwards, it was my next choice. And I have queues in there because basically I still need something to sort of buffer the amount that comes in, because even Lambda, when you scale it, you need, like, it doesn't go immediately. So shove things in a very simple queue, and then from there I can have workers that sort of pull things off the queue and scale those workers as fast as I possibly can. And then yeah, so I think some of the interesting things that are in here for you guys is probably not like the codec stuff, but what I've ran into with the codec stuff. So audio is a fun one. If you try to put, like, because we tried to use codecs that we knew that we could render on all, like play on back on a bunch of different devices. So it needed to support like old iPhones and computers and iPads and everything. So we knew H.264, AAC, those are the two things that we know, they're good, we can use these things. And you can do those in HLS, in TS segments. But then if you try to do AAC audio in TS segments and you like render new audio on each of these pieces, your offset times on the AAC that's no bueno. You get like little audio popping when you're listening to the video, like you just hear popping in between each of them. That's because the AAC has this weird offset timing stuff. If you use some other codec, it would probably be okay. AAC is just it's a shitty experience. So what I ended up doing is that I had all of those static segments that had audio on them, and that audio didn't pop. So I just took the audio from those segments and put those on my video, and then it was fine. So it worked. I didn't do any weird muxing with it, so it was still fine. None of the weird offset time was being added to these AACs anymore, so I could just literally shove it on. I don't fully understand why this works, by the way, because I'm not an expert in this. But I'm pretty sure that's how it's working, so you guys can tell me if I'm wrong about that one. I also mentioned spiky traffic being really hard. Basically, when an email campaign comes in, this is what I see. Basically, that 314 is like a web request saying like 314 people in 1 minute have clicked that link to go render your email. Each of these videos that I needed to render had several thousand frames that I needed to then render at the same time. So multiply 314 by several thousand, and that's how many frame workers I needed in a minute. My thing when I built this did not use Lambda, and this did not work very well. I was at least a little bit clever in that on my manifest worker, it's the one that's responsible for inserting the pieces in the right order when it's told or it can see that a piece has been rendered. So in my manifest worker, I had a timeout that was basically said, if I haven't finished this piece within say 20 seconds or something, then I'll just like fill the static chunks in and then we'll come back to this later. But then at least the user gets a video. So when I first shipped this out, it wasn't going to be personalized video if it failed, but it would at least be a video. And they make it like a second or two of buffering on the front end because like I still had that like static content prefix like at the beginning. And even when I shipped them the manifest, like when the request comes in, that doesn't necessarily mean that the person's already at a video player. All that means is they click the image. That then will take them to a page that will be on the company's website, which gives me like 5 seconds buffer time because none of the sites that they've been hosting these things on are good. And then I then have time, like that 5-second window, plus then our player needs to load, plus then they need to click the video thumbnail. So I've got like 5 to 10 seconds of literally just before the user even clicks play on the video that I can have plus the static content of the video. So I figured 20 seconds and then I'll render some static stuff if it doesn't work out. So yeah, it blew up, but like at least they got to watch videos. I just got lots of error logs, so less fun for me, but at least they got a video. Nowadays, we don't have to worry about that as much because we also found through this experiment that if the user ever is on a video player and it buffers for like 10 seconds, they leave, or they refresh, or they do something. Like, yeah, like they don't stick around to watch the video because they either think, well, the Wi-Fi's shit, or this video's shit, and they're not interested and they leave. So at this point now, if it's not done, I just delete the manifest, and the next time they come in, I can just regenerate it, because that's the benefit of rendering it in real time, is that now I don't need to worry about all the storage costs, because I only store these videos for like 30 days, basically. That's mostly GDPR requirements, so that we can say, well, yeah, because you have, like, if someone comes in with a GDPR request saying, please forget me, you have 30 days to delete your anything there. So we just delete everything after 30 days. We don't have to worry about it. It's like, yes, you requested that, we'll be right on it. Don't need to do anything. So that's nice. It's a good feature. And then if they come back in a year, like if you render out like a whole MP4 and then you have to store that, if they come back in a year, you still need that video. Here, it's like, well, we just deleted the manifest. We'll just re-render it, no problem. Saves us a bunch of money at that point because we're not storing it for the whole time. And the other nice thing about this is that in my worker design, I have a video worker. So when a request comes in, if you have like a video where you've got like a first name and person's company, a lot of the stuff that people render this for would be, say, like a university's admissions program will be like, thank you for joining this program. Here's like a mock diploma of like your name on here with our school name. Like the program is sometimes in there, but the names are also like, if you send it out to 20,000 people, you're gonna have a lot of named first name collisions. So you can reuse the section of the video that has the name in it. So I do. I use any of the segments that are the same between all of them. I just see as Derek, great. I don't have to render it, so I don't. So that's kind of nice as well. That was a nice side benefit. One of the other things that I ran into, which was really fun, right now I'm using Dynamo. I'm curious as well if anybody's using different cloud providers, if you have another solution for this. Basically, when I render all the frames, I need to store them somewhere just for a little bit, and then give them all to the piece worker. And it's like, say, it's 24 frames per second. I rendered like 1 second, 2 second chunks. It's not going to be a lot, but it's enough that I can't just store it in Dynamo or in SQS because those have fairly limited caps on what you can shove in the message payload. So initially what I was using was Redis. Redis keys sizes didn't have a huge restriction on them, so I was literally going with the frameworker and just shoving the rendered frame into Redis. And then later on the piece, I was just pulling those out, and I would expire them really quickly. I didn't have to worry too much about it, because Redis was basically, I could say, like, give me an enormous Redis cluster. I didn't even need that big, actually. I think it was only like 32 gigs. And I didn't run out of space, because they would expire so quickly. But the problem is that I had is when you insert really big keys into Redis, it's not really designed for that. And so when you get a spike like this, where it starts inserting like hundreds of thousands of frames into Redis, your master node gets write capped, and so your CPU spikes to 100. All the new frames that are rendering are trying to insert stuff into Redis, and they can't. And then your queue backs up. And so now your Redis stuff is like spiked at 100%. Nothing's going in, nothing's coming out. So it's basically just you flatline. And that wasn't a good experience. So now I just store it on S3, and there's a little bit extra latency, but at least it works. So. Yeah, it was an interesting one. And then, yeah, the classic, like, ECS is fast, but it's not. It's faster than Lambdas. But then when you need to, like, get more containers, like, really fast, then it's not very fast. They're getting a little bit better now with their capacity providers, but even still, like, it's on the order of minutes, which, as you can see, is not fast enough. So I use Lambdas, which are slower, obviously, but I can scale those out a lot faster. And they've also done some provisioning around Lambdas as well. You can keep them warm. Right now, I've done some sort of hacky thing where basically Lambdas have a warm-up cost time, and I just want, like, I know I don't get a lot of requests every now and then for campaigns where it's like part of like a warming campaign marketing effort sort of thing. So like, if someone comes to your site and they download a white paper, you want 3 days later, you want to send them an email with a video in it saying like, so you read the white paper. Thank you so much for reading the white paper. Here's some video with some more information of other stuff. And then you put their name in it so they'll actually watch the damn thing. Those are the nice kinds of like more steady traffic side of things. functions. So I have a Lambda warming function that basically just submits a video every like 5 minutes or something. Whatever the Lambda like expiry time is, I just took a minute less than that, and I send a video that often so that it keeps my Lambda warm. So that I can always have Lambdas running. Yeah, and then like ECS also has like Fargate. Sorry, I should explain these. ECS, Elastic Container Service, it's just Amazon's version of Kubernetes before they actually then supported Kubernetes. And then the other one that I mentioned was Dynamo, which is basically just really dumb storage, like key value storage. So, cool. Yeah, that's most of that. 15 minutes on the dot, so nailed it. Any questions? Yeah.
I got one of these videos.
Oh, did you? Excellent. Did it work?
With my name on it. I
There you go.
But I wanted to. It's just that my day is crazy.
No, I totally get it. Yeah. I did mention like most emails when they go through is like a 5% click-through rate. It's even lower for when it doesn't have your name in the damn thing.
It was a person with a whiteboard, small whiteboard.
Ah, yeah. Yeah, the classic one that I showed you at the very beginning. So that might actually have been someone that literally recorded themselves doing it. We also have a version where we do it as the company side of things, and those are more for like really cold outreach stuff. So.
I was half expecting you there to say, oh yeah, that's me behind the whiteboard.
Yeah, and some days it does feel that way, yeah, where I sit there with this and it's like, please, God, this is the 13th take, just work.
So how do you test that scale? How do you figure out?
When it breaks? Yeah, send it out to 20,000 people, you find out real quick it breaks. So we did that with an internal campaign first, and I had like on the manifest side of things where like I had the backup sort of things that if this didn't get anything from where it's expecting to see information after 20 seconds, it writes down the static when I put that in there. So when I first built the system, they would at least be able to get a video, which is really inspiring when you sell it to your boss and being like, don't worry, if it doesn't work, it's still it's not personalized, it still just gets a video. It's like, yeah, but we built this to be personalized though. I know, but it still works. It didn't sell very well, I guess. So yeah, we sent out like 2 different campaigns. Then the first one, they sent out to like 500 or 600 people, worked amazing. And then the next one they sent out was like way bigger and then failed miserably. And then after you get that little tail of like once you got down to like here, I was able to like recover the system and most of those started to go through again. So if you stay under the capacity of what Redis was capable of, my stuff was able to render it out in time and everything worked. It was just that initial front load that I couldn't handle. So trying to figure out what that was and then how big we needed to scale the ECS to handle that kind of stuff. And then seeing the money figures that came alongside scaling a cluster that big was like, yeah, let's not do that. And so we went with Lambda instead because then I don't have to run boxes the whole time. And yes, the Lambdas were a little bit slower, but we cheated in other ways in terms of like making sure there's enough static content at the beginning of the video. Or if we're sending this out to an email campaign, we do the thumbnails ahead of time, and as we do the thumbnails for when they send out this email campaign, as we're doing the thumbnails, we pre-render whatever personalized stuff is in the first like 15 seconds of the video, so that we can guarantee that that first section of the video is going to be static, even if there's personalized in here. We've already rendered it ahead of time, and we only store it for 30 days, and it's only like a couple seconds that'll be in here that are personalized. So that whiteboard one where it's like right at the very beginning of the video, that'll be like right at the beginning. We'll render that as soon as the thumbnail's rendered. And it still only takes us like 10 to 15 seconds to render those. So basically someone's like, if they're reaching out to a cold prospect or if it's an automated server or something, they'll do that to request the thumbnail. So it's like, give me a thumbnail that I can put in this email that has the person's name in it. So as they get the thumbnail back, it's now inserting into an email. They might type out some copy or the email gets sent out. That takes a couple seconds to actually get to your inbox. If you're a real keener, you'll open it and you'll click it within like 3 seconds. That's still I've already rendered that stuff. So, yeah.
What bit rates and how many levels?
One level. I do 720, nothing else. Basically, it was trying to make a compromise between mobile and desktop. if we considered doing multiple levels, but we didn't see enough demand for it. Basically 720p was good enough, and if you wanted higher quality side of things, we also have like the other product that uses the Adobe stuff. It just can't be done in real time. So
close to megabit.
Oh, I don't even remember anymore. Sorry, I honestly don't remember that.
Is a piece analogous to a segment?
Yes.
Oh, okay.
Yeah. I'm mixing terminology a lot because, as I said, I'm not a subject matter expert. But I like shut. You should look at the code. It's got everything in there, all the different kinds of segments.
So at the end, what you're looking to optimize is money, that cost to.
So yeah, the cost side of things wasn't as big a concern. It was more stability for us. We wanted to make sure that when we send out a personalized video that it does actually get personalized, and optimizing the generation portion of it as well. Like when we got a project, like an After Effects project from a customer, I'm sure that you guys have experienced, if you ever try to render something, you can render it and it'll take like 5 minutes, and if you spend like just like 30 seconds optimizing a couple layers so you don't have to, like, if the text layer for the iPad was like this big, and then you render the text to be the entire size of the damn frame and then shrink it down, like you're rendering a lot more pixels than you ever need. So if you just optimize just a little bit of time and say, I don't need it to be this big, I really need it to be that big, so I'll render it about that big and then like do whatever manipulations I need to do. Those are the kinds of optimizations that we actually care about, because that means that we render faster. It means that we don't run into memory issues on the Lambda side of things, because Lambda is kind of capped on how much memory they have available to them. So if you have, that was the other reason for quality. If we go try to do 1080p and try to render stuff out in using these Lambdas, and you have a lot of complex stuff being done and really unoptimal layering side of things, then you end up running into memory issues, or you end up getting to the point where it starts swapping a lot more than it should, and so it just takes too long. So those are the kinds of things that we really try to optimize, more than cost. Lambdas don't tend to run that expensive.
GPUs?
On the GPUs?
GPUs? Are you using GPUs?
No.
Wait, so After Effects type thing, does that usually add like GPU acceleration libraries or anything?
So, I mean, After Effects does have some GPU acceleration depending on the effects that you're using, but like 90% of the stuff is going to be CPU based anyway. So we didn't see any performance benefits, like not big improvements on the general projects that we're doing. But there are some that use FX where GPU is definitely helpful, but a lot of the stuff is not optimized for that. If you have GPU optimized stuff, I'm totally down.
Okay. This text distortion should be fast in the GPU, right? What is that? Oh, I guess it'll do the 3D, like, make it look like, perspective distortion.
Because it's a texture.
Yeah.
So.
Yeah.
If you take a rectangle and you rotate it in 3D space, it should be fast.
Yeah.
Do you send the emails yourself?
Oh, okay. Yeah, no, me separately. So I think the way that we've done it in the past is for our own internal campaigns, yes, but for clients, they tend to have their own like marketing systems that they'll send them through. So what we do is we have like the ability to export a CSV, where you've given us a CSV of all the client information that you want us to render, and then when you export it, we give you the same CSV back with another column that gives you an identifier that you put on the URL or on the thumbnail, and that identifier will then tell us which version of the video you're trying to watch.
So you can't throttle the email rate. It seems like it's straightforward.
I know, right? Yeah. So I've done that to our own marketing department, but I can't control other marketing departments.
Like, throttle the.
Could you not? Yeah.
So, are you using any of the tools used in dynamic ad insertion?
Okay, yeah. So there was 1 or 2 companies that we've worked with in the past that tried to do ads, but those generally didn't tend to align with the businesses that we normally work with, and so they churned. They went to other places that do support ads. Our player doesn't really do ads. You could manipulate this stuff for items for sure.
I mean, use the dynamic and insertion approaches to personalize.
Oh, okay, got you. Like with discontinuities in the HLS side of things.
To just do the static like a video and then dynamic
Mm-hmm.
treat it as an ad.
That was where I got the audio popping. Because as soon as you put discontinuities in there, it treats it as like, okay, I'm abusing the shit out of the decoders in web browsers because they really don't care too much about timestamps and offsets. Which is good because I like fudge the crap out of the offset timings on my video stuff to just sort of like, it's about this, work with it. So yeah, you would cry if you saw it, I'm sure. So yeah, the discontinuity flag would allow you to do that, but it's not seamless playback in a lot of browsers. Generally, what you end up hearing is either a slight pause or a pop. And so I've just not had good experience with trying to get, like even with discontinuity tags, to get it to properly put the content in sequence. And discontinuity tags also were not consistent from one browser to another. The decoders in the different browsers were not super thrilled with it. Safari was better than the other ones because probably they implemented the shit. But everyone else was sort of like not as great.
So would you modify the content to make sure the dynamic part does not have continuous audio?
Yeah, so that was another tactic that we've used for other campaigns where, like, for instance, like personalized audio, which I didn't do for this one, but we do support personalized audio. We would get that to render out someone's name, but it sounds really computery. So what they did in the video is they have a Furby say your name, and then we distort it a little bit, and then it's like, wow, that's really creepy. But it said your name, and you heard it, like, so, yeah. There are ways that you can sort of like hang a lantern on it, so to speak, or just like make it so that there's not there. I tried to do that with one of our videos where I wait for like the audio levels to like go down quite a bit and then cut it, and I still heard it a pop. Now maybe that's because I'm listening for it and I know what it sounds like, but yeah, your ears are so ridiculously sensitive compared to your eyes. Your eyes forgive a lot. Your ears will hear a lot more than you think. That was my experience with it.
Maybe use a clicky sound.
Just put popping everywhere in the video, and then like, yeah, what is with this popcorn machine?
Yeah, exactly. What are the things that bummer?
Yeah, exactly, yeah. That's a great idea. Yeah, no. Cool. Yeah, that's
Yeah, did you guys, you or your team, or Jared in general, do the parser for the After Effects input?
Yeah. Yeah, that was fun.
Was that started for this project specifically?
Yeah, I think I might have glossed over it real quick. Yeah, so like then do all that stuff outside of AE. So like by all that stuff, I mean like a tiny subset
Yeah,
of operations, just a couple.
Yeah, sure.
Like one of the things that they do, which is really fun, is fast box blur. It's their like recommended go-to blur within After Effects for when they say if you're going to use a blur, use this one. And then if you go to the Wikipedia entry for like how to implement fastbox blur, and you do this, and you're like, okay, cool, should be identical. No, not at all. It'll be like subpixel values for blur, and I'm like, what? How? So yeah, they basically, yes, exactly. They have, I'm sure they have a team of people that work literally on blur, but this was just me, so I was like, it's about the same. Use your best judgment. So yeah, there's a few things that I do that are not identical to the way that it's done in After Effects, but as long as it's close enough, especially with something like blur, it's not noticeable. So the difficulty that I had was literally when it goes for subpixel values of blur in After Effects. Like how the hell do I approximate that in my stuff? And go from there.
Cool. It's not just you that hates AAC. Most home theater receivers for some reason don't support it. So
Yeah.
clearly a bunch of audio people also don't like it.
At some point, I'm sure we will have some other audio codec that we can all love and use everywhere.
So I was supposed to replace MP3.
Yeah. Yeah, it doesn't happen yet.
I can do a demo.
Oh, hey! Yeah. I tell you based on who's in the video whether it's personalized or not.
So, yeah, drop to the video.
Ooh, fancy. There you go.
Later here from Vidyard, I want a quick video to introduce myself. Did you, the team, ever consider
He personally made
using
that
video
for
like
you.
this for
And now you want some part of it. He'll follow up with you in a couple of days. Cool. Thank you.
So another round of applause for our two speakers, Eric and Tim. And the thing that, you know, there's such a big, the two ends of the spectrum, I would say, between like we have subject matter experts who literally wrote the spec, and we have the other end of the people, you know, playing the videos and the player side, and I think this is why, you know, Waterloo is a great community for video, and yeah, so thank you all for coming. Have some more pizza, have some beer, have some water. Yeah, and hopefully we'll see you guys in a month.
Cool. Thanks, Chris.
Thanks, guys.
Thanks, Chris.